Okay. Yesterday I introduced about the position and rotation and homogeneous transformation matrix. And today I will introduce about relative transformation and absolute transformation. Okay. This is about the order of multiplying homogeneous transformation. If you multiply homogeneous transformation like this, you already saw this multiplication yesterday. So this index is erased and this B index changed to A. So result is same as ACT. So in this homogeneous transformation, the basis was B coordinate, but it changed to A coordinate. So we can change the basis of the coordinate system by combination of homogeneous transformation matrix. But you can also think about the reversed multiplication of these two matrices. So if you multiply like this, how can you think about this? So the order of multiplication is very important factor to calculate homogeneous transformation. So the result is not same. So these two matrix is absolutely not same. So the order of multiplication is very important. So let me think about the relative transformation and absolute transformation. Relative means we use some relative basis. So if you multiply this homogeneous transformation as post multiplication. Post multiplication means when you multiply T1, B, and B, C, T. So if you multiply this one and next, if you multiply this one, you can change relatively, you can change relatively the coordinate system. It means when you write down this homogeneous transformation, you can multiply in here the position matrix based on B coordinate. So the left part has base coordinate A. But when you use this transformation, you should multiply the position matrix in B coordinate. So this homogeneous transformation means you change it, the basis from A to B. So because the base coordinate is changed from A to B, you should multiply position in B coordinate. But if you post multiply in here, B, C, T, then this in this position, in here, we should multiply position based on C coordinate. So firstly, in here, the base was A coordinate. And in here, the base coordinate changed to B. And in here, the base coordinate changed again as C. So you can think about this one. So when the first time, the basis of the base coordinate was A, and by multiplying this one, you change it, the base of the coordinate as B. So you relatively change it from A to B. And if you also multiplying and you multiplied the right side, this we call this one as post multiplication. So in the post multiplication, we multiply the homogeneous transformation at the right side. So in this case, we also change it, the base coordinate from B to C. So as I already told you, in here, we should multiply position information based on the C coordinate. So in here, we can think about the transformation is based on the moving frame. The moving frame means the original frame was A and it moved to B, and this one is moving frame. And based on this moving frame B, we changed again to C. So we change it from A to B, from B to C. So this means relative transformation. So relative transformation follows the rule of post multiplication. And the Euler angle, when we describe the angle of the space, there is two kind of general method to express the angle information. One is Euler angle, and the other one is lower pitch yaw angle. And there is also Cottonian angle interpretation, but we will explain about that later. If you already took the class, robotics class, undergraduate student, in the undergraduate student, you already know about the Euler angle and lower pitch yaw angle. So Euler angle means Euler angle follows the relative transformation, and lower pitch yaw angle follows the absolute transformation. Okay, this was the explanation about the relative transformation. Let's think about absolute transformation. I will tell you about this absolute transformation using the same homogeneous transformation multiplication. Let's think about PC. So position information based on the C coordinate. And if you want to change this base coordinate from B to C, you should multiply BCT. Then this will be BP. And so in here, we multiply the homogeneous transformation in the left side. And let's think about one more time. If you have position information in coordinate B, if you want to change this one to A coordinate, you can multiply ABT. Then this one will be AP. So if we combine this one, we can write down like this. Yeah, this one is the same matrix equation you already saw in the relative transformation. But we can think about this two homogeneous transformation was multiplied in this side. So when we interpret this equation, we think these two homogeneous transformation was multiplied in this way. And also, we cannot interpret these two homogeneous transformation is multiplied at the left side. Those two interpretation is correct. This one is also correct, and this one is also correct. But the way of interpretation is different. So if you interpret these two matrices multiplied in this way, you interpret this one as relative transformation. But if you interpret these two homogeneous transformation is multiplied in this way, you interpret the transformation as absolute transformation. So let's think about this one again. If we interpret this equation, these two homogeneous transformation was multiplied in this way, you change the base coordinate from C to B. And you also change the B coordinate to A. So we can interpret this one is same as A, B, T, P, P. And also we can interpret this one as A, C, T, C, P. In both cases, we transformed the P position based on the A frame. It means this A frame is, if we assume this A frame as the fixed frame, we can think about these two transformation is about the transformation based on the fixed frame, because the A frame is fixed frame. So this kind of interpretation means absolute transformation. So sometimes we call this fixed frame as absolute frame. So in the same manner, in this kind of transformation, we call absolute transformation, because this A matrix is fixed and B and C is moving frame. So if we transform some position using the base of the fixed frame, then we call this one as absolute transformation. So in this case, the multiplication is pre-multiplying. It means we multiply homogeneous transformation to left side. And this kind of this kind of angle representation is roll pitch yaw angle. So the important thing is when you think about the transformation, this equation can be interpreted relative transformation and also interpret as an absolute transformation. And this one always both correct. So both correct. So we can interpret this way and also interpret this way. So there is two kind of interpretation. So always there are two kinds of interpretation in the combination of homogeneous transformation. So this is the one example. So Euler angle. Euler angle means relative transformation. So if we rotate g-axis and then relatively transform along y-axis and then relatively transform x-axis. And this one is GYX Euler angle. And this equation will be same as XYG roll pitch yaw angle. So for the more detailed explanation, I will bring some supplement material. Let's think about this one. So this one is the class material of intelligent robotics, which is the robotics class in undergraduate students. In this class, I used this slide when we explain about the GYX Euler angle and XYZ roll pitch yaw angle. Firstly, the GYX Euler angle, the order of the multiplication is Z and then Y and then X. So in this order, 1, 2, 3. So this matrix multiplied in the right side. So this one is post multiplication, and which means this one is relative transformation. So let's multiply these three matrices. Then the rotation matrix becomes like this. And let's see this transformation process. Firstly, rotate z-axis about alpha angle, and then this one becomes moving frame. Firstly, this one was fixed frame, and when you rotate alpha, this axis become moving frame. And along this moving frame, we change beta angle along this moved y-axis. And when we rotate beta angle, this z unit vector becomes like this, and x unit vector becomes like this. And then we rotate again gamma angle like this, alpha, beta, gamma angle, and then this y-axis become like this, and z-axis become like this. So when we rotate the axis, we follow the base using moved frame. This is very important thing. So when we change the angle at the next time, we use the base of moving frame. So this is relative transformation. And if we think about the absolute transformation, let's think about XYG roll PTO angle. In the absolute transformation, we use left side multiplication, which means pre-multiplication. So in the order of X, Y, G, X, Y, G, and we multiply like this. As you can see, this equation exactly same as this one. So the result of these three matrix, the result matrix of this three matrix multiplication becomes same, because these two matrix is same. The result transformation, this one, and resultant transformation, this one, is exactly same, or exactly same orientation. So even though we interpret this transformation as relatively and absolutely, we can think about this transformation as two kind of interpretations. So as a result, G, Y, X Euler angle exactly same as X, Y, Z absolute roll PTO angle. Because of this one is relative transformation, which is multiplying right way, and this one is absolute transformation, which is multiplying this way, and also this order of multiplying is reversed. 1, 2, 3, 1, 2, 3. Because of this kind of interpretation, we have same result matrix like this. So this one is very interesting and very funny situation. But because the multiplication, the order of multiplication is important in homogeneous transformation, these kind of things happen. So let's return to the review of the robotics. And in the robotics class, in the undergraduate robotics class, we already learned about the kinematics and DH parameter. DH parameter is Denavit-Hartenberg parameter. So this one is UR5 robot, which is developed by Universal Robot. So it is cooperative robot, which is very famous in the world. And about this robot, I described the axis and the link length and axis offset. And by using this information, we can make this table A alpha D theta. And this 4 parameter is DH parameter. So if we fill this information, we can make forward kinematics forward kinematics transformation matrix. If we know forward kinematics, that means we have this matrix as a function of theta. So if we multiply this homogeneous transformation result, so if we multiply these 6 homogeneous transformation matrix, then becomes 0 to 6 transformation matrix. So in this transformation matrix, there is rotation matrix from 0 to 6 and position matrix 0 to 6. So from here we can get the position of end effector based on the 0 coordinate. And also we can get the orientation of the end effector based on the 0 coordinate. So this homogeneous transformation is exactly indicate the forward kinematics information. So if we know this transformation, we can say we have forward kinematics equation. So that's it. So this one was the summary of undergraduate robotics class. Actually, there is more about the inverse kinematics. And also, we already learned about the velocity kinematics. And also, I teach in the intelligent robotics the velocity profile method, like trapezoid method. So if you want to know about this, you can check the internet GitHub homepage. So if you search GitHub space 동일C, I have GitHub account. In here, you can check the intelligent robotics. In here, I uploaded the Python library for kinematics and dynamics. Let me show one example. Example 5. This file is Python Jupyter Notebook file. So you can see like this beautiful code. So in the Jupyter Notebook, you can write down the code, and also you can write down some explanation comments. So I already made the library named Intelligent Robotics. So I imported as IR, and we also use SymPy and NumPy library. So in this example, I will show about the forward kinematics and inverse kinematics of two-link planar robot. So this one is two-link planar robot. In move in the planar space with two link and 2 degree of freedom. In here, I calculate the forward kinematics using DH parameter. So this one is DH parameter. You already saw A alpha, D theta, and from this one we can get the homogeneous transformation matrix. And if we multiply these three things, we can get forward kinematics equation. So this one is forward kinematics equation. And in here, we get the velocity kinematics, which means Jacobian. In here, we can get the space Jacobian like this. So when we calculate the Jacobian, we already we also use the IR library. So in here, we can calculate angular velocity and linear velocity, and then in here we can get the Jacobian from the velocity information. And then we also calculate the inverse kinematics solution. This one was force kinematics and velocity kinematics, and then inverse kinematics. So in the inverse kinematics, we should calculate it using numerical method. So for using numerical method, we imported numpy, and actually this one is the analytic solution. So this one is not the numerical one. So sorry about that. This part is analytic inverse kinematic solution. So because of this two-link planar robot is very simple to calculate the inverse kinematics. So we can simply calculate the inverse kinematics using analytic way. But in the case of more than 3 degree of freedom, we should use the numerical method. So let's see this one. When I gave the target position as -1.3 and 0.5, then it can touch like this by using this angle. So this one is inverse kinematics. So inverse kinematics means when we give the position, we should find the angle of the rotation. So we found the angle of the rotation based on the target position. But if we use numerical inverse kinematics, we can solve many kind of high degree of freedom robot manipulator. So as I told you, more than 3 degree of freedom, we should use numerical inverse kinematics. So in here, we describe how to use the numerical inverse kinematics. So in the numerical inverse kinematics, we should know about the space Jacobian J. We already calculated this one. So using this one, we can inversely solve the angle, the inverse angle to touch the goal position. This numerical inverse kinematics solved by iteration. So it iterate some calculation, inverse calculation process while it touched some small error boundary. So this kind of method, we also called it Newton-Raphson method. So we use Newton-Raphson method. Newton-Raphson method. So by using this method, we calculate numerical inverse kinematics. So as you can see, we got the same result as the analytic solution. And also in this part, if we move this two-link planar robot from here to there, we have some trajectory to follow some path. So we can give this position and then this position. Then if we give these two position, it moves like this way. So this one is very dangerous situation to handle the robot because it instantaneously moves like this. So we should give the BR point to follow this, to follow some trajectory, and then it should touch the goal position. So we generated very smooth curve to go this target position from the original position, like this way. This trajectory is trapezoidal trajectory. So by using this, we can get the angle to go the target position. This one is position information, and this one is angle information. By using the numerical inverse kinematics, here we calculated the angle to follow this trajectory. So as a result, you can see the animation to learn this one. So so that's it. This one was the summary of intelligent robotics, which is the undergraduate robotics class. So more information you can check this one. There is 7 examples, and there is a open source library, the intelligent robotics.py, which is composed by myself. And if you did not take the robotics class, you should study more hardly about this one. But if you took the robotics class, you can simply check these examples. And in our class, we will use the Python and Python Jupyter Notebook. So about the Python, you should install using Anaconda. Using Anaconda, you can install Python and Jupyter Notebook. About this one, you can check YouTube or many internet information how to use this one. So I will not explain about this. So you can do this one by yourself. And also there is a YouTube video like this. So if you search modern robotics in YouTube, there is a internet class presented by Kevin Rich, which is the composer of modern robotics textbook. So
There is the answer to this question.
So if you want to study more about the class, you can also see this YouTube video. So in this video, he explained very compactly about the class. So this is very good video lecture. So you can see this video and also you can see my video. So you can double check how to understand the modern robotics class. So the first class is done. So you have lecture activity. So you should write down this class material. So you should upload the result of your class activity, and that's it. Let's meet next week, and don't forget to upload the introduce yourself in the KakaoTalk group chat room. Thank you.